In the previous video, you've had a look at a demonstration in which when you measure the potential difference across a battery directly, that value is slightly higher than the value which you get when you measure the potential difference across a battery that is connected to a resistor. So let's look at why that happens. But before that, let us quickly recall the analogy that we were talking about in the last video, which is that if I have a battery connected to a resistor, this thing is analogous to a pump. So this is my pump here that lifts water from this level to that level, and then it could be connected to some parallel pipes, and then some pipe that descends down, and another parallel pipe that just takes the water back to the pump. Simple, right? Now I had told you that this section of the pipe is like the resistor, because as the water moves from this end to that end, it loses all its potential energy. Similarly here, when the resistor when the current moves from one end of the resistor to the other end, the charges lose all their potential energy while moving through the resistor. So that energy might be dissipated as heat and light and other forms of energy. So yeah, and I had also told you that there is no potential drop across these parallel pipes because the height of the water does not change, so the potential energy should not change. That is similar to these wires that have no resistance, across which the charge does not lose any energy because it has no resistance and it flows without any loss of potential energy. Now what we did not talk about in the last video was the pump and the battery. So when water moves from here to here, obviously there will be some friction between the various components of the pump and water. Now that friction will obviously oppose the flow of water, and so this pump will have to do some additional work to take the water from this level to that level. So it will have to overcome that slight bit of friction between water and the components of the pump. And so if we, let's say, supply this pump with some electrical energy, obviously we use electricity to power pumps, right? And let's say I am using 20 joules of energy for every 1 liter of water that I raise from this level to that level. Now during this process, the pump, because of all that internal resistance to the flow of water, it loses 1 joule of energy for every 1 liter of water that is being raised, and this 1 joule of energy may be released as heat and sound. So you might have heard the sound of pumps working and pumps heat up and all that energy losses. And what we end up getting is the water that reaches the top only has 19 joules of energy for every 1 liter. So every liter of water that reaches the top, that 1 liter of water has only 19 joules of energy. So that is so if we apply that same thought in this case of the battery, let's say this battery has the ability to do 3 joules of work for every coulomb on every coulomb of charge, which simply means 3 joules of work for every coulomb of charge simply means it has a capacity of 3 volts. But because the battery is made up of matter, and so matter means it is made up of atoms, and those atoms would collide with electrons passing through the battery. So the battery also has some resistance. Now just like this resistor here, even the battery has some resistance called its internal resistance. And so from now onwards, whenever we are looking at such circuits, we'll not just count the resistance of the resistor itself, but we will also have to count in the resistance of the battery, which is called the internal resistance. So the battery will have to spend some energy for every coulomb of charge to overcome this slight resistance inside the battery, and so the net potential difference that it is able to create across its terminals would be slightly less than these 3 volts. It would be 2.9 volts or something. I mean, it could be anything lower than 3 volts, right? And that 0.1 volts would be lost as heat, energy, and maybe other forms. It is basically heat, generally heat. So that is the simple idea here of internal resistance, and I hope you can understand the analogy here. Now if I just have to give a slight mathematical touch to the whole thing, to make it just more solid. Yeah, so what I can do is, let's say the internal resistance of this battery is R, and the resistance of this resistor is capital R. Now what I can say is, I know by Ohm's law, so voltage equals IR, V equals IR. Now this battery has a thumb of 3 volts, or the total, so it can deliver 3 joules of energy for every 1 coulomb of charge, which means its net thumb to do work is 3 volts, right? 3 joules of energy per coulomb. And this net thumb that the battery has, or the net ability to do work for every coulomb of charge, is called its EMF, or the electromotive force of the battery. It is not a force actually, it is just called EMF, but it is actually the net energy per coulomb that the battery can supply. So that's the EMF. Now this thing has to be equal to, so obviously when the electrons are inside the battery gives the electrons 3 joules of energy per coulomb, or 3 volts, right? So this 3 volts is similar to the 20 joules of energy that is being supplied to the pump, right? It has to use all that energy because energy cannot be destroyed. So if we are talking about that 1 joule of that 1 coulomb of charge, that 1 coulomb gets 3 joules of energy. Now that 1 coulomb of charge has to spend that 3 joules of energy as it moves through the circuit in this loop and comes back to the same spot. How does it lose that energy? Well, first of all, it has to travel through the battery itself, and because the battery has some internal resistance, it does lose some potential energy. How much? Well, let's say there's some current in this circuit I, which will be same throughout the circuit, and the potential drop across this resistor would be simply I, the current in the circuit, times the internal resistance of the battery, IR. So that is the potential drop across this battery, or the energy that the electrons lose across the battery itself. So this term IR here is very much similar to that 1 joule of energy that is being lost inside the pump, right? It is very much similar to that value, plus it not just, so the electron not just loses this IR amount of energy, but it also moves ahead. So this is 0 resistance, assuming that is perfectly conductive, and then it reaches this conductor here, and now it has to lose some more energy, which will be obviously I, the current in the circuit, times R, resistance of the second resistor. So that is it. 3 volts equals I times the internal resistance of the battery plus capital IR, which is the resistance, which is the potential drop across the second resistor. Now let's say I don't connect the resistor to the battery, but instead, so let's say I have this battery here, I leave the wires here. So now let us say I want to connect some device that requires 3 volts of potential difference to function properly. Can I use this battery here to power that device that requires exactly 3 volts? Well, the answer is no. Why? Because remember this 3 volts is the EMF of the battery. This is the net capacity of this battery to deliver the energy. So this battery can deliver 3 joules of energy for every 1 coulomb, but all that energy, all that 3 joules for every coulomb is not available for use for that device, because some of that energy has to be spent here to take the charge from here to here. So what we are left with is not 3 volts but slightly less than 3 volts. Okay, so now let us so if somebody asks me how much voltage can this how much net voltage can this battery deliver here, so how will I find that out? Well, this term here is what tells me the net voltage that this battery can deliver. So this is the net kind of usable voltage that I can obtain by using this battery. This term here tells me the loss of energy for every coulomb of charge that occurs inside the battery itself. So this term IR, so R is the internal resistance, and this term IR will tell me how much heat is lost for every coulomb of charge that passes through the battery. So that is the wasted energy. this was the total energy per coulomb, this is the wasted energy per coulomb, and this here tells me the amount of energy per coulomb left with me for the use. So if I connect, let's say, some bulb here, I hope that's how you draw it, yeah, just bear with me. So if I connect some bulb with this battery, how much voltage is being supplied to the bulb? It's not 3 volts, it's IR volts. So whatever that number would be, it depends on the current in that circuit. So you'll have to take R and capital R and small r and solve for that. But the basic idea is that it's not 3 volts that is being supplied to the battery, it's only IR amount of potential difference that is being supplied to this bulb. And yeah, this this voltage here that can be used by any device that is connected to the given battery is called the terminal voltage. Terminal voltage. I hope you can understand that, right? Terminal voltage. Why is it called a terminal voltage? Because the battery has 2 terminals, and this is the voltage that you get across the 2 terminals when you connect it to some circuit. So these are the 2 terminals of the battery, and if you connect something, this is the potential difference across these 2 terminals. This is the EMF, that is the total energy that every coulomb of charge gets in this battery, but some of that is wasted. It depends on the internal resistance of the battery, and this, the net leftover voltage, net leftover energy per coulomb, is called the terminal voltage, which can be used by the device that is connected. So now coming back to the demonstration in the last video, when you were connecting the resistance to the battery and you were measuring the potential difference across the the terminals, what you were actually measuring was the terminal voltage. Why? Because there was some current flowing in this circuit, and you had obviously connected the ammeter in series, right? You connect your ammeter in series, so there's some current flowing in the circuit, and due to that current flowing, remember, so see that wasted amount of energy depends on the current. So due to that, some amount was being wasted, and you were measuring only this amount of voltage, which is the terminal voltage, and that would be less than if we remove this circuit and we simply measure sorry, you were not using an ammeter, you were using a voltmeter in parallel. Sorry, very sorry for that slight mistake. So if you were measuring the potential difference across these 2 terminals, but the problem was there was some current flowing in the circuit, and due to that current flowing, so if the current flowing is higher, I will be larger, and so IR will be larger, and so the amount of energy per coulomb being wasted would be higher, and so the net amount of energy that is being left would be lower for you, and so the terminal voltage that you measure in this case would be lower than the voltage that you get if you remove this circuit and you take a multimeter or a voltmeter and try to measure the voltage of the battery directly, because in that case the current in this battery flowing would be lower, and so the energy per coulomb wasted is lower, and so you get a closer value to the EMF. And obviously, if you're wondering how do we measure the EMF, well, we'll deal with that in the coming section topics, but the basic idea is we have to find out some way by which we can reduce the current flowing through the battery to 0, and then if the current flowing would become 0, the energy wasted is 0, and so the terminal voltage becomes the EMF, but that's for later. The basic idea in this video was to explain you internal resistance, EMF, and terminal voltage, and what's the difference between terminal voltage and EMF and what they mean. That's it for this video.